Let us continue the discussion on turbomachinery, and we will continue the centrifugal compressor and then follow with the other compressor. So, this is where we actually stopped in the discussion in the last lecture. So, we are talking about the diffuser and vaneless diffuser and vent diffuser, and this is the schematic of the geometry where we are talking about the gap, which is a vaneless gap, and the whole idea is that these are the different radius and R 4 is the mean radius of the diffuser throat. So, what now we are trying to look at is that air will pass pass through these passages, and finally, we get the proper pressure rise. So, that is how it happens. If the air does not enter smoothly, that is one of the issue here. If air does not enter smoothly, then what will happen? There would be flow separation, and because of the flow separation, there would be performance degradation in the compressor. So, what is important is that design of diffuser become important. So, this is an important task, and out of that obviously vane is one component, second is the throat. So, these are the two components. So, there could be vaneless space between the impeller and the diffuser. Now, because the air leaving the impeller has to traverse through this gap, its directions may change, because it may not remain same leaving the impeller tip. So, to fluid the correct inlet angle of the diffuser vanes, so you need to consider this vaneless passage here in the design consideration. Now, since no further energy is supplied to the air once it leaves the impeller, so the angular momentum must be conserved in this vaneless passage, and what is that? You can neglect frictional losses, and the process is isentropic. So, how we will go about it? So, theoretically there should be V theta r is constant. So, this is your angular momentum with no external force. Okay. So, this gives you an idea how the V theta actually varies. It is 1 by r, and one can see the V theta will decrease as r goes up. So, the tangential compressor velocity decreases for impeller tip to diffuser vane. Now, the flow passage in a channel of constant depth, if we consider. So, the channel with constant depth. So, what would be the area then? Area would be 2 per pi r V, and the mass flow rate would be m dot is rho a V r. So, this one can write 2 pi r B, that is area rho V r. So, one will get V r is m dot divided by 2 pi rho r B. So, now here again you can see if r increases, this will get you that V r decreases. So, the radial component of velocity also decreases from impeller tip to diffuser inlet, and also when r actually increases, so overall V also decreases. So, some diffusion takes place in the Venn space also. Okay. So, this is what is quite important, that even in that Venn space that you get some sort of a diffuser or the diffusion process to take place, which means the flow field velocity that also decreases. However, one can see when the density actually increases as V decreases. So, that because your pressure actually increases, and hence V r is proportional to 1 by r. So, this variation depends on the variation on density also. Hence, one has to calculate this by using the continuity equation. So, now if you have V r and V theta at the leading edge of the, so V r and V theta at the leading edge of the diffuser vanes are calculated, the vane angle can be also estimated from the conservation of angular momentum. How? Let us see. So, V theta 2 and r 2 would be V theta 3 and r 3. So, V theta 2 is the tangential velocity at the impeller blade tip. So, already we can obtain that V theta 2 will be u 2 is r 2 omega. So, this one can get from the analysis of the impeller. Now, what we can get V theta 3 is V theta 2 r 2 by r 3, which is let us say equation 1, and one has V 3 square equals to V theta 3 square plus V r 3 square. So, that is let us say 2. Now, energy equation, using energy equation one can write T naught 3 equals to T 3 plus V 3 square by 2 C p, which is nothing but T naught 2, because this is adiabatic. Now, T 3 is T naught 2 minus V 3 square by 2 C p. So, that is let us say get this. Now, we have said this process is isentropic. So, which means no loss. So, we will get P naught would be P naught 3. So, one can write P 3 by P naught 3 is T 3 divided by T naught 3, which is gamma by gamma minus 1, which is let us say equation 4. And we have one more equation which is coming from density, which is P 3 by R T 3. Now, B is the depth of diffuser passage. So, what will happen? A 3 equals to 2 pi R 3 B, and mass flow rate would be rho 3 A 3 V R 3. So, which will get me V R 3 is m dot by rho 3 A 3, that let us say equation 6. So, here we get, if we look at these equations, there are 6 unknown, which are V theta 3, V r 3, V 3, T 3, P 3, rho 3, and we got 6 equations too. So, but equation is not independent. So, there are two ways one can solve it. So, number 1, one can combine the equation to form a single algebraic equation of one variable, solve that equation. So, basically it is a combination process. So, one can combine that, and in a single algebraic equation and to obtain one variable, and then from there you back calculate the others. Or one can do, you can solve iteratively. So, if someone wants to check this out, he may or she may wish to do that. You can take this one as a task of some sort of an homework and try to see that how it can be done. Or third approach one can do, let us say we can first some guess value or choose some VR3. So, you start with VR2 equals to V3, then use equation 2 to 6 and you obtain VR3. So, let us say this is step A, this is step B, then at step C we can repeat this A and B till convergence, and then to get VR3. So, once you have that, then you can find out tan alpha 3 is VR3 by V theta 3 and tan alpha 2 is VR2 by V theta 2. So, if it's Venn-less or constant with diffusor, then alpha 2 will be alpha 3. So, that is what you can get to going ahead with the design process. Now, then we can look at the throat width of diffuser channel. So, this is another aspect of it that one can do. So, air entering the diffuser at its throat is also at an angle, and hence the throat region also has to be designed accordingly. So, that is why this is important. Now, the throat width actually that depends on flow angle and mass flow rate. So, that is what it is. Again, so one can do that using the conservation of angular momentum. We can write that V theta 4 R 4 equals to V theta 2 R 2. From here we will get V theta 4 is theta 2 R 2 by R 4. Now, again V square is V theta 4 square plus V R 4 square, and we can write T 4 is T naught 2 minus V 4 square by 2 C p, that is let us say equation. So, this is what we are writing, because again it is an adiabatic. So, T naught 4 would be T naught 2 would be T naught 3. So, that is what we could write, that kind of situation. Now, again it is an isentropic flow. So, P naught 4 would be P naught 3, which would be P naught 2, because it is isentropic. Now, you say P 4 by P naught 4 would be T 4 by T naught 4 gamma by gamma minus 1, and you have rho 4 which is P 4 by R T 4. Okay. So, one can start at the first case or first approximation, you can say one can neglect the thickness of diffuser vanes. Okay. So, once you do that, then it becomes quite simplified, and one can write A r 4 is 2 pi r 4 into B, and from there we will write V r 4 is m dot by rho 4 A r 4. So, one can do iteration up to this to get V r 4. So, the iteration can continue up to this and to get that. Now, if you look at that velocity triangle, so this is how it will look like. So, this is V 4, this is alpha 4, this is V theta 4, this is V r 4. So, my tan alpha 4 is V r 4 by V theta 4, and my m dot is rho 4 A r 4 V r 4 equals to rho 4 A 4 B 4, from where we get A 4 is A r 4 B r 4 by V 4, that is 14. Now, V r 4 by V 4 is sin alpha 4. So, we will write that A 4 equals to A r 4 into sin alpha 4. Now, let us say if n is the number of diffuser vanes. So, alpha 2 equals to alpha 4 is valid in the throat region. Okay. So, I can write H B n is A 4, from where I will get H equals to A 4 by B dot n. So, from here you can see the throat area is calculated. Okay. Now, also one can note here the length of the diffuser passage also depends on the maximum possible diverging angle and the required pressure rise. Now, up to throat, the vanes may be curved to suit the air flows. Okay. And after the throat, the air is along the passage and controlled. The walls of the passage could be straight. Again, when it leaves the diffuser or after leaving the diffuser, the air can be combined and put to a single combustor. Now, of different diffuser vanes may be fed into diffuser combustor, which is common to gas turbines, and the design of vane and throat are at certain operating condition. So, other conditions apart from this, the other conditions the flow will not be smooth. So, one can to find out all these details, basically how much flow will deviate or what kind of deviation that could be there. So, one can use detailed CFD analysis to find out that thing. Okay. So, this is how the design portion of this component to be looked at. Now, once we have that, then the next important parameter is the compressor characteristics. Why this is important? Because end of the day this characteristics curve would determine what would be the operational range or what is the region where this or any particular combustor should work or operate. So, beyond that point, so the reason is that you have different conditions or operating conditions. For example, you have altitude and there you have temperature, density, pressure, Mach number, you have power level. So, all these are conditions which are coming from the real system or the real engine, where the engine inbuilt with the compressor is going to operate. So, as we have already talked about several times, that the main idea behind the compressor is to compress the air or incoming air. So, it essentially pressurize the incoming air dynamically, and the pressure rise depends on mass flow rate for a particular, it is a particular geometry. Okay. Now, performance of any compressor may be specified by curves of delivery pressure and the temperature and also the rotational speed. So, these are all depends, all these things depends on inlet conditions, physical properties of air. So, if one has to look at the complete detailed analysis, either it has to be done through proper experimental analysis in a rig with proper or detailed instrumentation, or one can go for the very high fidelity computational approach and to look at that. But any experimental procedure, these are expensive with kind of detailed equipment or instruments which is required to get this kind of curve. So, and at the same time any computational analysis also could be expensive quite a bit, because these are all dynamic machines with rotating components at certain RPM and rotating. So, the best approach which could be there is a simplified approach of dimensional analysis. So, this is what one can do and find out these things. So, using dimensional analysis, the complete characteristics of a compressor can be presented using two curves and with the variations of the other parameters. So, P is an important variable, and also, but density is connected with P. So, if we choose P and T as independent variable, then density can be specified. Now, for a highly turbulent flow of a compressor also, viscous effects are very small. So, that means high Reynolds number case, where the viscous effects are small. So, we can neglect that. So, the viscous effects would be neglected. So, the non-dimensional parameters would be the non-dimensional parameter space can be defined based on that. Now, the function would be R T naught 1, R T naught 2, P naught 1, P naught 2, mass flow rate, these are 0. So, D is the where R T one can look at is a V square by 2, which is sort of an measure of energy, and the other parameters like n is rotational speed, where d is the characteristics dimension. So, characteristics dimension. So, typically one can take the impeller dia. So, that is what one can consider. 2 is the compressor outlet, 1 is compressor inlet. So, we have essentially, if we look at this non-dimensional parameter space, we have 1, 2, 3, 4, 5, 6, 7. So, we have 7 variables. Now, we invoke the Buckingham pi theorem. So, Buckingham pi theorem. So, if we invoke that, we got 7 variables and we have 3 fundamental units, which are m, l and t. So, we need number of non-dimensional groups would be 7 minus 3, which is 4, and these non-dimensional groups could be like P naught 2 by P naught 1, T naught 2 by T naught 1, m dot r T naught 1, d square P naught 1, n d r T naught 1. Now, when you consider a machine of fixed size, so the machine of fixed size and consider the specified gas R. So, once we say that you take a fixed size machine and specify the gas, then R and D, these are invariable. So, this R and D can be omitted from these non-dimensional groups, because we have considered it or chosen a particular gas. So, this will become then, once we omitted that thing, this will become P naught 2 by P naught 1, T naught 2 by T naught 1, m dot 2, T naught 1 by P naught 1, n by T naught 1, which will be 0. Here you can see in this non-dimensional group, one is that m dot T naught 1 by P naught 1, which is non-dimensional mass flow, and then this is n by T naught 1, which is non-dimensional rotational speed. So, these are in this non-dimensional group, these are the non-dimensional 2 parameters that would be important for further analysis. One is the non-dimensional mass flow rate, another is the non-dimensional rotational speed. But if one look at it, they are, this is just for note, they are not truly dimensionless. Okay. Since the constants are omitted. Okay. So, one can get the characteristics plot by plotting each of these group with respect to another while keeping the other parameters constant. Now, just to note here, this m dot by R t is d square p, which will be rho a v R t by d square p. So, this is p a v R t by R t d square p, which is proportional to v by R t, which is Mach number, and n d by R t proportional to v by R t proportional to Mach number of R. So, m f is the flow Mach number and m r is the rotational Mach number. So, these are the two different parameters that we get. So, we will stop it here and continue in the next session.